Good morning, everybody. I am Mirko Piersanti from the INFN University of Rome Tor Vergata. Here, we present a description of the whole sequence of the event from the sun to the ground, as well as a detailed analysis of the observed effect of the August 25, 2018 geomagnetic storm on the Earth's environment by using a multi-instrumental approach. We studied the ICME propagation in the planetary space up to the analysis of its effects in the magnetosphere, ionosphere, at ground. This kind of analysis is in the context of the space weather. The most probable source for the CME is a filament eruption observed in the solar surface, here highlighted by the yellow circles, whose heliographic coordinate is a latitude of 16 degrees and a longitude of 14 degrees. We can project the CME velocity and estimate its radial speed, obtaining a value of 175 km per second with an error of 45 km per second. We propagated the CME in the heliosphere as highlighted in the figure at the bottom right side here, with the characteristic computed above and considering its interaction with both solar and with both slow and fast solar wind for the whole duration of its travel. We estimate its arrival time at 1 AU on 25 of August at 60 with an error, UT, with an error of 3 hours. In fact, the observation of solar wind parameters at L1 point confirm our results of the arrival of the ICME. Here, on the right figure, we displayed the solar wind density, solar wind speed, proton temperature, interplanetary magnetic field, and its direction, angular direction, in the ecliptic plane and in the direction that is parallel to the Earth dipole. It can be easily seen by the increase of all the solar wind parameter, here highlighted by the red dashed line, of the arrival of the interplanetary shock on August 24 at 7:18 UT. It was followed on the 25 of August at 16:31 UT by the arrival of the ICME, as highlighted by the red shaded region. The ICME is followed by the arrival of CIR that we identified by the increase in the solar wind density and temperature and of the interplanetary magnetic field, and by rotation of the north-south direction of the interplanetary magnetic field. The CIR lasted until the end part of the 26th of August, where the region of high-speed stream lasted until the end of August. At ground, this perturbation produced sudden impulses at almost 30 minutes after the passage of the interplanetary shock at 1 at L1 orbit, a main phase characterized by a geomagnetic storm whose main phase is characterized by a very low value of the CMH index of almost 200 nanoteslas, a very long recovery phase that lasted till 31 of August, and a very large high latitude auroral activity that was characterized by an AE index greater than 2000 nanotesla. In order to evaluate the magnetospheric response to the arrival of the ICME, we first of all try to model the magnetospheric field line via the Tsiganenko-Sitnov model. Here we reported in the upper panel the magnetospheric field line configuration before and black lines, and after red lines, the arrival of the interplanetary shock. It can be easily seen that the magnetopause was strongly compressed, and its subsolar point moved from 10 Earth radii to 6.8 Earth radii. Lower panels shows the response of the geosynchronous orbit satellite in terms of the magnetic field measurements. Panel B and C shows the X component of GOES-14 and GOES-15 respectively. Panel D and E shows the Y component, and panel F and G shows the Z component. In this case, we are showing the observation along the GSM reference frame. The variations along the X direction confirm the stretching of the magnetic tail field lines. The variation along the Y component during the main phase confirm the twisting of magnetic tail field lines, while the variations along the Z component confirm the concurrent contributions of the compression of the magnetopause and the action of the enhanced ring current. This scenario is confirmed by the simulation of modified Tsiganenko-Sitnov model that is represented here by the red dashed lines. In fact, during the SI, the magnetic field were well reproduced by the magnetopause current that strongly compress the magnetosphere. While during the main phase, the magnetic field were well reproduced by the concurrent contribution of the ring current and the tail currents. In order to evaluate both magnetospheric and ionospheric response in the ionosphere, in the Earth ionosphere, we used a low Earth orbit satellite that is newborn. It is called the CSCS satellite. Here we show the three components of the magnetic field observed by such satellite along the geomagnetic north-south direction, the geomagnetic east-west direction, and the geomagnetic vertical direction pointed downward. In this case, we removed the Cal6 internal model, internal core plus crustal. By applying the magic model, Piersanti et al. 2019, we were able to discriminate between ionospheric and magnetospheric origin contribution in the magnetic field observation by CSCS satellite. As expected, the greater variation is along the horizontal component. The upper panel shows the ionospheric contribution, while the lower panel shows the magnetospheric contribution. The magnetospheric contribution is dominated by the ring current contribution. In fact, the X direction strongly decreases during the main phase, while it is dominated by the ring plus the tail current during the recovery phase. It is confirmed by the simulation of the Tsiganenko model that was tested along with the same characteristics that we applied for GOES satellites. The ionospheric contribution instead is dominated by the DP2 ionospheric current systems. In order to evaluate if the presence of ionospheric irregularities, we used the plasma density observation by the Langley probe that was mounted on board the CSCS satellite. In particular, we evaluate the rate of density, that is a parameter derived directly from the electron density recorded by the satellite. The figures shows the ρD values for August 25, August 26, and August 27 that was separated for night-side semi-orbits and day-side semi-orbits. Can be easily seen that higher ρD values occurred during the main phase of the storm for both nighttime and daytime orbits, while ρD comes back to lower values on August 27 after the main phase, the end of the main phase. This behavior can be explained in terms of the presence during the main phase of ionospheric irregularities, especially at auroral zone and equatorial zone. To understand whether this significant increase of irregularities could have caused space weather effects on navigational systems in terms of the loss of lock on GPS, we have considered vertical total electron content data measured by another LEO orbit satellite, that is World constellation. In this case, only VTEC data with corresponding elevation angle of 50 degrees have been taken into account. We have considered vertical TET data recorded by each of the three satellites A, B, and C of the Swarm constellation and corresponding to each PRM satellite in view. In order to let a possible reader sure about what is a loss of lock, we made a direct comparison between the rate of TAC index evaluated for the August 2018 geomagnetic storm and the more known St. Patrick's 2015 day storm. It can be easily seen there's no loss of lock, that is a separation of the routing, has been found during the August geomagnetic storm, contrary to what happened, for instance, during the St. Patrick's Day storm, where the VTEC measurements highlighted many loss of lock, as highlighted by the blue circle here. In order to evaluate the ground response of the geomagnetic storm, August geomagnetic storm, we selected 82 ground magnetometer using intermagnet dataset. We analyzed the ground magnetic response over the entire globe, and here the red and green stars represent two magnetometric arrays along almost the same meridian, used to study the effect of the geomagnetically induced current at ground that represents the most serious space weather effect at ground. We applied, first of all, the magic model to remove the geomagnetic field of internal origin in order to focus on both the magnetospheric and ionospheric contribution. The main contribution of this external field are the polar ionospheric currents, the top polar electrojet, and the magnetospheric currents, that is, the ring current. Here we report the SIM8 index on the left, while in the central panels reported maps showing the effect due to eastward and westward electrojets. These two polar current systems are always present, but their intensities increase during the main phase of the geomagnetic storm. The right panels show the effect due to the ring current that is responsible for the decrease of the magnetic field intensity at low and mid latitudes. The increasing of the ring current westward direction produces a strong depression of the horizontal field magnitude during the main phase occurring on August 26. In the days after the perturbation, the ring current effect is still visible, although its amplitude rapidly decreases. To evaluate the GIC effect, we calculated the GIC index using the method of Tozzi et al. 2018 over the European and North American sectors at different geomagnetic latitudes and along almost the same geomagnetic meridian. In particular, we focus on Europe and African sector, and it is represented by the red stars, and on the American sector that is represented by the yellow stars. The results show that along the north-south direction, we found that the GIC index is extreme along the European sector, while is very high for the North American sector, reaching its absolute values for latitude, geomagnetic latitude, greater than 70 degrees. While for the east-west direction, the GIC is between high and extreme. The GIC index is between high and extreme, reaching, also in this case, its higher values at almost 60-70 degrees in latitude. These results are in agreement with Pulkinen et al., Villanen and Piriola, and Piersanti et Carter results. So, we can say that the solar event occurred on August 20, 2018, has been capable to increase the intensity of the various electric current systems that flows in magnetosphere and ionosphere. Such currents activate a chain of processes which cover a wide range of time and spatial scales, and at the same time, activate strong interactions between various regions within the solar terrestrial system. The long reconnection process at the day-side magnetopoles lead to an increase of the magnetospheric circulation, to an injection of particle into the inner magnetosphere, and, more in general, it provided free energy which was stored in the magnetosphere and led to a worldwide magnetic disturbance. Such disturbance lead to an increase of currents in ionosphere that was accompanied by the roll activity and by a shift an equatorward shifting of the auroral electric jet, and of course to an increase of the ring current. From a space weather point of view, the amplitude of the GIC reached values corresponding to high and extreme risk level, between 60 and 70 degrees in the north sector of geomagnetic latitude. Finally, we want to remark that this kind of comprehensive analysis play a key role to better understand the complexity of the process occurring in the Sun-Earth system during a geomagnetic storm that determines the geoeffectiveness of solar activity manifestations. Thank you very much.